Good. So welcome everyone. I'm Shubhra Bhattacharjee from ICTS and I'm here on behalf of the Colloquium Committee. We are really happy to be a part of this program and by embedding the ICTS monthly colloquium in this program, which helps the ICTS researchers to sort of gain a bit more from all the exciting programs that are going on. So with that, I'll hand over to Professor Rukmini Monti and she would introduce the speaker today.
Okay, so hello everyone. It's a great honor and privilege for me to introduce today's speaker, Professor Yvonne Wong, and she is a theoretical physicist working at the interface of particle physics and cosmology. Her research primarily concerns using the observations of the universe to probe fundamental physics. Professor Wong obtained her BSc Honours degree from University of Melbourne in 1999, and she obtained her PhD degree from the same university in 2001, just 2 years after her BSc degree. After several postdoctoral positions in the US and Europe, including DESY, Hamburg, Max Planck Institute of Physics Munich, and CERN, she was named a junior professor at RWTH Aachen, Germany in 2009. She returned to Australia in 2013 and is currently an associate professor at the University of New South Wales, Sydney. With this, let me just invite Professor Wong to deliver our colloquium on neutrinos in cosmology, a match made in the heavens.
Okay, so thanks for the introduction. And so I'm telling you about neutrinos in cosmology, which also happens to be the title of the 3 lectures that I'll be giving at this the program, Understanding Understanding Universe Through Neutrinos. So this is sort of like a preview, if you like. Okay. Now, normally you wouldn't think about neutrinos and cosmology together. Wouldn't say them in one sentence because, after all, neutrinos are one of the lightest and most weakly interacting known particles of the Standard Model. Whereas cosmology is the study of gravitation on the largest observable scales, the study of the universe. And yet, when you put these 2 things together, then there's a very interesting prediction that comes out of it. And that is the cosmic neutrino background. Okay, so this is a thermal background that was made 1 second after the Big Bang when the universe was extremely hot. Okay, so attaining a temperature of 10 to the 10 Kelvin, so much hotter than anything that we know in stars, etc. Okay? So essentially, what I'll be telling you in the next 50 minutes is all the fun things that we can do with this cosmic neutrino background. So I'll start with a brief introduction about neutrinos and cosmology before moving on to talking about the neutrino background itself and observational evidence for this background. And in the second half of the talk, I will be mainly talking about the idea of measuring neutrino hot dark matter and therefore neutrino masses via cosmological observations. And if I still have time, I'll say a couple of words about other non-standard properties that you can measure of the C nu B. Okay? So I'm not entirely certain about the audience that I have, so I just prepared a couple of slides on the Standard Model. So this is the Standard Model of particle physics, which is the most self-consistent and highly tested fundamental theory of nature, as we know, as yet. It has a bunch of matter particles, which are these fermions, and there are 3 generations of them, split into quarks and leptons. And the model also describes 3 of the 4 fundamental forces, namely electromagnetism, the weak nuclear force, which is responsible for nuclear decays, and the strong force, which is responsible for binding nucleons together into, passing the nucleons and nucleons into nuclei. Now, 3 forces are basically described by these force carriers, and so that's basically what we have. Now, the neutrinos are here, down here. These are fermions. There's 3 generations of them: the electron neutrino, the muon neutrino, the tau neutrino, and they are very light. Okay, sub-electron volt mass is what we think. And if you're not familiar with these units, let me tell you that the mass of the electron is about 500 keV, mass of a proton is 1 GeV. So relative to these particles, the neutrinos are extremely, extremely light. They're electrically neutral particles. Okay, so it means they don't feel any electromagnetic forces. They are also not strongly interacting. And in fact, the only force the neutrinos feel is the weak force. Okay, so that's what we mean when we say they're weakly interacting. Now, of course, this standard model is not a complete theory. There are tons of things it doesn't explain. These are some of the things that most people would name that are missing from the standard model, like particle for the dark matter. It doesn't incorporate gravity, doesn't explain things like antimatter, matter asymmetry, etc. But let's remind ourselves that, the standard model, we only know it to energies above TeV. So there could be extensions to this model beyond these energy range that will explain some of these shortcomings that I mentioned before. But that's not what we'll talk about today, because what I want to highlight is that even if we just confine ourselves to those energies where we know the standard model works, there are still some very interesting things that it predicts in a cosmological setting. So at this point, I'll move to cosmology. And this here is a schematic of the history of the universe. Okay, so roughly what we understand the universe, how it has evolved since the Big Bang to the present time. So the Big Bang is somewhere here, and all the different stages that the universe has evolved through, down to the present time, which is here. Now, the central feature of this hot Big Bang model is the expansion of space. Okay, and so if you imagine that space is expanding as we move forward in time, then if you turn the clock backwards, what it will tell you, what the conclusion you will come to is that back in the ancient times, very, very ancient times, the universe would have been a very, very small place. Okay, and the more you compress something, the hotter it gets. Okay, so the early universe in the first moments was a very, very hot and dense place. Okay, so hotter than anything that you can imagine. Now, what this means is that those particle physics processes that you normally wouldn't think would happen under everyday conditions could have happened in the extremely early times. Now, most of these processes, so that's what I call the particle physics era. So that's basically shortly after the Big Bang, extending all the way to, I'll define it as, say 100,000 years after the Big Bang. Okay, that's particle physics era. Now, most of these particle physics processes are kind of transient in the sense that you might produce some very heavy particles, but then they decay away and leaving nothing behind that we can observe today. But every now and then, there will be a process that will leave behind something that is interesting. And those things that are left behind are called relics. Okay? And they survive to the present day, so we can observe them. And if we just embed the standard model into this expanding universe picture, then there are already 3 types of relics that are just predictions that we can come up with. The first is a cosmic microwave background, and that's a thermal background that was formed about 400,000 years after the Big Bang. Neutrino backgrounds 1 second after the Big Bang, that's the focus of this talk, and there are also some light elements that are formed maybe about 20 minutes after the Big Bang, so in different stages. Now, let me just say a couple of words about the cosmic microwave background since it's so famous. So this is a cosmic microwave background, and it's a thermal photon background formed, as said, at about 400,000 years after the Big Bang, when the universe had a temperature of about 0.2 electron volt. If you're not familiar with these units, that's about 3,000 Kelvin. Okay, so this is a background in photons. And it has, so roughly what happens is that you go back to this early times of 400,000 years when the universe was 0.2 electron volt in temperature. And what's happening is that you have basically a soup of particles, electrons and around, and photons as well. And there's so many of these photons and electrons that what's happening with the photon is it's basically just doing a random walk in this electron soup. And so it will be scattering of the electrons, get bounced, walk this way, walk that way, going all over the place. So in other words, at these very early times in the universe was opaque to photons because they're random walking. Okay? But then as the universe expands, and with expansion comes cooling, then at some point, the temperature of the universe will drop below 0.2 electron volt. And what happens below 0.2 electron volt is interesting, because now the energy of the electrons that are also in this path here will be low enough that they will be captured by protons and form bound states. Okay, so instead of having ionized hydrogen protons around and electrons floating around, now you have these neutral bound states. And these neutral bound states are not very good for photon scattering. Okay, so in effect what happens is that at these low temperatures, the photons are no longer doing a random walk, but they can free stream. Okay, they can just go in a straight line to infinity. And so at this stage down here, we say that the universe is transparent to photons. And that eventually becomes observed as the CMB. Now, today the CMB has a temperature of about 2.73 Kelvin. I say about because actually the actual measurement is more like 2.725 plus or minus 0.001. So it's measured very well, the temperature. And that was first discovered back in 56, was it 1956? And that led to the Nobel Prize awarded to Penzias and Wilson. And since the 1990s, we also have a very good measurement of the energy spectrum of the CMB, which turns out to be the most perfect black body we've ever measured. And that was measured by COBE, the Fire-S instrument on COBE. And the COBE instrument, COBE satellite also had another instrument that was able to measure fluctuations, spatial fluctuations of this background. And what they found were these 10 to the minus 5 angular fluctuations in the temperature, in the CMB temperature. And this measurement led to a Nobel Prize for John Mather and George Moot in 2006. And since then, there have been 2 more generations of these CMB and anisotropy measurements by WMAP and more recently by Planck. Okay? And there was another Nobel Prize awarded to Peoples for predicting these temperature fluctuations, amongst other things that he did. Okay, so that's the CMB. Now, what about the CNUB? So the CNUB is actually kind of similar to the CMB, except that it was formed at a time much earlier than the CMB. So CMB was formed at a time 4,000 years after the Big Bang. The neutrino background, on the other hand, was formed 1 second after the Big Bang. But the physics is kind of similar. In this case, the interaction that is responsible is the weak interaction because the neutrinos are only able to feel the weak force. So again, you have this picture here where we are looking at the universe at a temperature above 1 MeV. Okay, so that's about 10 to the 10 Kelvin. And that was the condition that was attained 1 second after Big Bang. Okay? So here what you have basically again is this picture of a soup, a primordial soup of particles. So you have electrons and positrons and also all the neutrinos floating around. And because the temperature was so high and these neutrinos are so energetic and the universe are so dense, even the neutrinos are able to do a random walk in this soup. Okay, that's something that you don't see anywhere in any stellar system whatsoever, not in the sun. Maybe in a type 2 supernova, but certainly not anywhere in the stellar system. But in the early universe, that was what was happening. Okay, you have neutrinos doing a random walk, scattering off the electrons and the positrons, and also scattering off other neutrinos. And so what you have is basically this kind of scattering happening at equilibrium rates. And again, as the universe cools, expands and cools, at some point, these interactions will become inefficient, okay? Because space expands and the particles are finding it increasingly difficult to find another particle to scatter on. Okay, so at a temperature less than 1 MeV, you have the situation where the CNUB is able to free stream, the CNUB neutrinos are able to free stream to infinity because the interactions are no longer efficient to keep them scattering, okay? And these neutrinos that free stream to us would be the CNUB. So some statistics, some standard predictions for the CNUB. Well, it's a thermal background, just like the CMB is a thermal background. But whereas for the CMB, you have a Planck spectrum, for the CNUB, because the neutrinos are fermions, they would be described by a Fermi-Dirac distribution. Okay, so a minor difference. There's also a very neat prediction from the standard model for the temperature of this CNUB, and it is related to the temperature of the CMB in this way. So there's a funny factor 4 divided by 11 raised to the power 1/3, and this is essentially something that is determined entirely by the standard model. It's related to essentially how many standard model particles that are relativistic at the time of CNUB formation. Okay, I can tell you more about this. If you come into my lectures, I can tell you exactly how this works. But anyway, for now, just have this factor. Which means that, if you use this expression, it means that the neutrino background temperature should be about 2 Kelvin today. Okay, so the CMB is 3 Kelvin, the neutrino background is a tad cooler, mainly because it was formed at an earlier time. Now, if I know the temperature of this background, and I know that these neutrinos are distributed by the Fermi-Dirac distribution, it's very easy to calculate what is the number density of these neutrinos today. And it is actually quite a large number. We're talking about 100 neutrinos and antineutrinos per family in 1 cubic centimeter. In this much space, there's 100 of them on average in the universe. You can also calculate very easily the energy density ratio of the CNUB to the CMB, and that also turns out to be something that is very close to 1. That's good. So what does it mean? Well, here is a picture called the Grand Unified Neutrino Spectrum, which I took out of this review. It's a physics report. And basically, this picture here shows you all the natural neutrino sources that we have in the universe. And what you see here is that the C nu B is way up here. It really is the most abundant neutrinos we have. Okay, in the actually one of the most abundant particles we have in the universe, just next to the photons, CMB photons. Okay, C nu B here, everything else has been detected, but not the C nu B. Okay, so then at this point, I'm going to ask the question, since there's so many of these neutrinos, can we detect the C nu B? After all, we've seen the CMB, it has collected 3 Nobel Prizes. Maybe we can do the same thing with the C nu B. So what can we do on that front? Well, as it turned out, it's very hard. And the reason it's very hard is obviously because the neutrinos are weakly interacting. It's hard enough to detect neutrinos as they are. So thinking about detecting some extremely low energy background, which is 2 Kelvin, what is that? That's 10 to the minus 4 electron volt. Yeah, that's really, really a non-trivial problem. But people think about this, people have thought about this. And the best idea so far, I would say, is still the one by Steven Weinberg, from Steven Weinberg back in the 60s, which was revived more recently by these guys and some other people. And the idea is very simple. And what you do is to make use of beta decay. Now, beta decay is just basically this process, some nucleus decaying into another nucleus, emitting in the process an electron and an antineutrino. So in my schematic over here, the yellow line here indicates the spectrum, the energy of the electron that is emitted. Okay, so this is the electron energy. I should have labeled my axis, I didn't. And that's basically a kind of spectrum, if you like. Okay? And if I look at the energy spectrum of this electron, this is what I would get for the first process. But if I'm able to find a process that would perform, a nucleus that would undergo this beta decay, then the same nucleus should also be able to capture a neutrino from the background. Okay, so that would be indicated by the second process. So you have 100 per cubic centimeter of neutrinos floating around, right, as I said. There are many of them. You can think about this beta decay nucleus capturing one of these neutrinos, and that triggers this process where it would go and turn into another nucleus N prime plus an electron. And if I ask what should the energy of this electron be, then it would turn out to be essentially this monochromatic line that is beyond the endpoint spectrum of the first process. And the gap between the endpoint of this first spectrum and the monochromatic line is essentially just 2 times the neutrino mass, okay? And basically what the point I'm trying to highlight here is that the idea of detecting the neutrino background, the cosmic neutrino background, is actually very closely related to neutrino mass measurement using beta decay. Okay. Now, so now we know that this process is, can potentially allow us to detect the C nu B. Let's estimate some rates. Well, actually, some people have done this. These people have done it. What they found is that if you manage to find 100 grams of tritium and then just let it there, sit there, and capture neutrinos, then you'll probably get about 10 events a year. Enough to do statistics. But the problem is that this is capturing the Karlsruhe tritium neutrino experiment, which is basically the flagship tritium beta decay experiment to do neutrino mass measurements these days. And guess how much tritium they have? That's 0.1 milligram, okay? Someone told me that there is actually 100 grams of tritium in the world. I don't know who made them, probably the Russians, but just considering how much tritium there is in Katrin, and comparing with how much you need to even get 10 events in this sort of experiment, it's clear that probably these kind of experiments not going to happen anytime soon. But there's one more thing we can play with, and that is the local neutrino density, the local neutrino overdensity. And that's basically any kind of gravitational capture that may lead to there being more neutrinos on Earth than the average prediction. Okay? Remember, the average prediction is 100 per cubic centimeter. But you can imagine that if you have massive neutrinos and they are falling into potential wells, then maybe you get more neutrinos than the average prediction. Well, you can think about, you can entertain that, but even then, if you want Katrin to be able to detect the neutrino background with an overdensity of neutrinos, it takes an overdensity of 10 to the 9 for Katrin to register anything, okay? This plot is extremely difficult to read, but essentially, this is the neutrino mass. This here is the overdensity that is required for Katrin to make a detection. And essentially, you need to be way up here in order for a detection, in overdensity, in order for a detection to happen. And some people have calculated the overdensity that is expected in the solar neighborhood. Actually, I did one of these calculations myself 20 years ago. And on average, you expect maybe the overdensity to be about 10 more than the average prediction. So we're talking about maybe 1,000 neutrinos per cubic centimeter as opposed to 100. But that's still way off compared to what is required for Katrin to detect the neutrino background. Okay, so the bottom line here is that it's a bit of a, it's a bit science fiction at the moment, hoping to use the speed of decaying nucleus process to detect the neutrino background. But still, it's not something that we shouldn't think about. But in the meantime, there are other ways to indirectly establish the presence of the cosmic neutrino background. Okay, and that's what I'll spend the next 35 minutes to tell you about. And the way to do that is to look at the imprint of the C nu B on the cosmological observables themselves. Okay, so here we go. Now, so basically the idea of looking for the C nu B in cosmological observables rests on the fact that if you have the C nu B sitting there, then it's a relativistic energy density at early times. And if you have a relativistic energy sitting there, then it will contribute to the expansion of the universe, because the expansion rate depends on how much stuff you have and the kind of stuff that you have in the universe. So this here is an expression for the expansion rate, so H, also called the Hubble expansion rate. And this expression here tells you how it depends on the different kinds of things that we have in the universe. So omega m here is basically the energy density in non-relativistic matter. Omega r is the energy density in radiation. This is the cosmological constant, spatial curvature, and you can keep adding to this list if you have weirder forms of energies. Okay, but this is the most basic expression I can write down. Now, if I ask, an A here, by the way, is called a scale factor, and that's basically a measure of how much space has expanded between two time points. Okay, and you can see these different forms of energy densities depend differently, evolve differently with respect to the scale factor. Now, for the C nu B, for C nu B detection, the energy density in relativistic standard model particles up to CMB formation times essentially is relativistic, okay, going into the radiation part here. So that's given by this expression. So you see the energy density in the CMB and the energy density in the C nu B. Okay, I put a sum here because there are several families of neutrinos. Now, what is common to do in the cosmology community is to parameterize this energy density in the C nu B in terms of a parameter called n effective. Okay, it's written like this. So in this expression here in the brackets, this stuff is, you times that by the energy density in the CMB. So 1 here is for the CMB, and all of this second term here in the brackets stands for the energy density in the neutrinos. And n effective here is sort of like the number of families of neutrinos, so roughly it's 3. But because ultimately this parameter here is defined as an energy density ratio, it's not an integer. And in fact, if you do the calculations properly, what you'll find is that this number is 3 for 3 families, and there are some percent level corrections due to various things like non-instantaneous decoupling, finite temperature QED, neutrino oscillations, etc., which I'll say more about in the lectures probably on Thursday or Friday. Okay? Now, so what we can do therefore is to try to see in our data, in our cosmological data, what value the data prefer for this n effective parameter. Okay, so this is actually a pretty old game, and in fact, the first paper to even consider using cosmological observables to measure n effective came out back in 1977 by these founding fathers of the field of astroparticle or particle cosmology. And what they were doing, essentially, they were looking at the expansion rate at the time of nuclear synthesis. So that's the process that gives us all these light elements that happen up to about 20 minutes after the Big Bang. And in particular, they were focusing on the helium-4 abundance, because helium-4 is an extremely stable nucleus, and most of the neutrons in the early universe get sucked up to helium-4, to form helium-4, and the amount of neutrons versus proton is highly sensitive to the expansion rate. So they were using helium-4 to see what they can say about N effective. And already back in 1977, what they found is that N effective has to be less than 5. Okay? So that was pretty cool, because that was, what was that? That's 20 years before Lab determined the number of neutrinos to be 3. Okay? And in modern days, of course, we have much better measurements. And this is analysis from 2018, where they found this N effective parameter to be about 3. Okay? So that's already a very nice piece of evidence that the CNUB is existing at the time of nuclear synthesis. These days, we also have another set of really good data for making cosmological observations, making cosmological inferences, and that is from the CMB anisotropies. Okay? So these two pictures here are the temperature and polarization measurements from the Planck CMB mission. And what you're seeing here in the first map are basically a map of the spatial fluctuations in the temperature of the CMB. And these are fluctuations that are 1 part in 100,000. Okay, so very, very tiny fluctuations. What's usually less discussed is polarization fluctuations. And you also see that the way the light is polarized is fluctuating across the sky. And the CMB light is polarized because Thomson scattering is polarizing. And if you have some spatial, if you have a quadrupole in a spatial, in anisotropies of the temperature, then Thomson scattering would actually turn that into an anisotropy in the polarization. So we have these two maps that are measurements from Planck. Now, normally what we do with these CMB measurements is to condense the information into these endpoint correlation functions. And the simplest of them is the 2-point correlation function. Okay, so you've probably seen this picture over here. That's the 2-point correlation function of the CMB temperature map. Actually, this is in harmonic space, so it's kind of like a Fourier transform. So we call this a power spectrum. And so you see here that basically this map here the information can be condensed into this power spectrum, which shows these acoustic peak structures. Okay? You can do a similar thing also with the polarization map, which is the one over here. And again, you see fluctuations represented on large scales over here, small scales over there. You could even cross-correlate the temperature map and the polarization map to give you a cross-correlation power spectrum. And in fact, these days, when we talk about a cosmic pi, where we have determined the dark matter density to be 25%, dark energy to be 75% and 70%, and baryon density to be about 5% of the energy budget, it really comes from analyzing the peak structures of the CMB. Okay. Now, back to the CNUB, back to N effective. Well, as said, the main effect of N effective on any cosmological observable is the fact that N effective changes the expansion rate. So this is also true if the CNUB is existing at the time of CMB formation. Okay, so at the time of CMB recombination, the effect of N effective is basically here in the damping tail. It's calculable. It's in the damping tail, and this picture here shows you the CMB temperature power spectrum in a damping tail for different cases. Okay, different N effective, I assume. And what you see here immediately is that the data really overwhelmingly prefers a value of 3. Now, this is a bit hand-waving. You can actually do your statistical analysis properly. And in fact, this is what the Planck collaboration found. They found that N effective is 3, essentially, to 10%. Okay? So that's completely consistent with what we should expect from standard model prediction. So that's pretty amazing, I would say, because, it's just a standard prediction. Okay? There's no fudging or anything like that. It just came out like that. So I think that's pretty cool. Okay, so halfway. So in the last 20 minutes or so of this talk, okay, no, that's a take-home message. No, okay, so let me just go through this first. There's a prediction of the C nu B. It's as fundamental as a prediction of a CMB. And direct detection is quite impossible at the moment, but we can see its effect in cosmological observables. So we know that there is a background. Okay, now let's move on to the next part, neutrino hot dark matter. Okay, so now we've seen that there's evidence for the C nu B, and we know that the standard model predicts there to be about 100 neutrinos and antineutrinos per cubic centimeter today. Yeah. Now, if these neutrinos have mass, and they do, and we know they do, because of neutrino oscillations, then they can actually contribute a significant fraction of the non-baryonic or dark matter density in the present-day universe. Okay? Because even though you have a background that was initially relativistic, as the universe expands and everything cools, these neutrinos will eventually become non-relativistic. And we expect any massive neutrino to eventually become non-relativistic. Okay? And once they become non-relativistic, they can start contributing to the dark matter. That's a fairly simple expression you can write down to determine how much energy there is today in neutrino dark matter, and it's given by this expression. Okay, so it's expressed here in terms of this reduced energy density parameter omega, and basically what happens here is that you take the energy density and then you normalize it to the critical density of the present-day universe. So this omega nu here is proportional to the neutrino mass, and there's some factors here, and you're going to sum here, which is summing over basically all neutrino families that we have. Okay. Now, we don't really know what this omega nu is exactly, and that's because we don't know what the neutrino mass is. But we do have some ideas about roughly what sort of numbers omega nu can take. So there's a lower limit on how small this omega nu must be. And that is because from neutrino oscillations, we know that at least one neutrino mass eigenstate should have a mass larger than 0.05 electron volt. So if I take this number here and then stick it into my expression down here, it's pretty easy to establish that omega nu will work out to be about 0.1%. So that's a minimum amount of neutrino dark matter that we should see in the universe today. On the other hand, we have an upper limit, and that comes from tritium beta decay experiments. And so you've seen this schematic before in the context of C nu B detection, but this time we're looking at the endpoint spectrum over here, and essentially what tritium beta decay experiments are trying to resolve is this little gap here between the Q value and the true endpoint of the spectrum. Okay, and we have Katrin, and they've been producing measurements, they've been doing measurements and producing results since the last few years. And as far as I know, this is the latest constraint they have published on the effective electron neutrino mass. And this is in the range of 0.9 electron volt. Now, this is a limit on just the electron neutrino mass. And we still have the mu neutrino and the tau neutrino. But at the same time, we know there's maximal mixing, large mixing, not maximal, large mixing in the, from neutrino oscillations. And so since in cosmology, what we really care about is the neutrino mass sum, to get an estimate of what this means for the neutrino mass sum, I basically just multiply this number by 3 to get 0.27 electron volt. And if I then put 0.27 electron volt into my expression for omega nu, what I'll find is that the maximum omega nu is about 6%. And so here's my prediction. I should expect omega nu to be between 0.1% to 6%. So relative to this cosmic pie of energy density that we have in the energies that we have in the universe today, what you find immediately is that this neutrino dark matter would be a subdominant kind of dark matter. So most of our dark matter would be cold, okay? So the usual dark matter that we talk about, and a little bit of it would be hot, coming from neutrinos. This is a pretty wide range still. So one way to improve it is for Katrin to return a better measurement from the top end. But as it turns out, it is also possible to shrink this range further by looking at cosmological observables themselves. And that's how it's done. Okay, so we could move to cosmological neutrino mass measurement at this point. Let me just remind you that people have also thought about cosmological neutrino mass measurements for a very long time. And the first paper on limiting neutrino masses with cosmology actually came out in 1972 by Kalsick and McClelland. And essentially what they did is to demand omega nu here to be less than 1 so as not to overclose the universe. And if you do that, you immediately get a bound of, on the neutrino mass sum of 24 electron volt, which of course today is kind of large on the large side, but still this is probably the first paper I'm aware of where people thought about using cosmology to limit neutrino masses. But of course these days we are a lot more sophisticated in our methods than just that one-line calculation. So what we do in modern times when it comes to cosmological neutrino mass measurement is to basically assess the impact of the C nu B on the inhomogeneities of the universe. So this picture here shows you the nearby galaxy distribution out to a redshift of about 0.2 as mapped by the dark energy spectroscopic instrument, DESI. Okay, they published their results recently where they found a deviation from lambda CDM, but anyway, that's not the topic today. In any case, this is the map that they have found of nearby galaxies. And as you can see here, it's not homogeneous. In fact, there's a certain pattern to the way the galaxies are clustered. So every dot here is a galaxy. There are filaments, there are voids, etc. So what we can do, therefore, is to study the pattern of this clustering to see if we get anything different if we change the amount of cold dark matter versus neutrino dark matter. Okay, so here is a simulation of exactly what I just described. So there are two simulations over here. In fact, the one is the one on the left is with 25% dark matter, and the simulation on the right actually has mostly neutrinos at 15% and 10% of dark matter. They start in exactly the same way with exactly the same initial conditions. But if you let the system evolve, what you'll find is the following. So simulation on the left is the one with cold dark matter only, and has a lot of fine details, a lot of fine structures. Okay, the one on the right, on the other hand, is mostly neutrinos. And what you see is that if you squint your eyes, the two simulations look sort of similar. Okay, but if you look in detail, this picture here is kind of empty. And it's really devoid of small structures. Okay, so you look at this bit here, it's kind of empty, but this bit here has a lot of tiny structures. And the reason for that is because of an effect called neutrino free streaming. Okay, now as I mentioned earlier, when you produce you form the neutrino background, it was a relativistic particle species at early times, but with expansion, these particles sort of slow down. Okay, so that they are technically non-relativistic today. But they're not non-relativistic enough. Okay? They're still coming with a lot of thermal velocity, which allows these neutrinos to fly away. Okay? So instead of falling into a potential well, which a cold dark matter particle would, the neutrino particle prefers to fly away because it has just way too much kinetic energy and no way to dissipate it. And if these neutrinos are not being captured by a gravitational potential well and flying away, then that's the situation that you will see where you get these empty void regions. Okay? Now, again, as with the CMB, we don't just look at these pretty patterns. What we do is to condense the information into a power spectrum, because it's easier to understand and easier to calculate. And this is what we get. This is a meta power spectrum. And the yellow line here tells you what the power spectrum is. The power spectrum corresponding to just a standard lambda CDM with zero neutrino mass. Sorry, the purple one is the zero neutrino mass. The yellow line, on the other hand, is a cosmology where I replace some of the cold dark matter with neutrino dark matter, so that my overall dark matter content is still the same, but now the ratio of hot versus cold is different. Okay, so now I have some hot dark matter. And what you see immediately is this pattern where these two lines are kind of, well, the same, overlapping on large scales, which are to the left. But as you go to the smaller and smaller scales, further to the right over here, you see a suppression of the power spectrum on these small scales. Okay, and this suppression is basically the way we quantify the amount of missing stuff on the small scales. Okay? And the amount of suppression is more or less proportional to the neutrino mass sum, which means that we can exploit this signature as a way to determine the neutrino mass. Because like the larger the suppression you get, the larger the neutrino mass sum, the larger the amount of suppression you will get. Okay. Now, there are many different types of surveys at the moment that are able to measure this power spectrum. So we have on the large scales, CMB, for example, primary anisotropies. Lensing is also able to, you can use it to measure this power spectrum. Galaxy clustering surveys, BAO, cosmic shear, that's gravitational lensing, cluster abundance, Lyman alpha, etc. So, different types of probes that are able to measure different parts of this power spectrum. Okay, so this is my schematic. This is an actual measurement that was, well, actually, it's done by different collaborations, but this particular plot here was compiled by the Planck collaboration. And so again, you can analyze this spectrum, test it against theoretical predictions to find out what the neutrino mass should be. Now, unfortunately, we haven't actually measured the neutrino mass this way, but what we do have at the moment is a lot of series of bounds on the maximum value that this neutrino mass sum can take. And at the moment, most of the bounds are returning numbers like 0.1 to 0.5 electron volt, 95% confidence, depending on exactly, you have a range of numbers because different analyses are done differently, assuming different backgrounds, assuming different hierarchies for the neutrino masses, etc. But still, it's about 0.5 electron volt, 0.1 to 0.5 electron volt. And if you compare this number here with what Katrin is able to do at the present, and then at face value, what you find is that this is, a factor of 6 tighter. The cosmological bound is a factor of 6 tighter at face value. Having said that, however, I want to give you this mandatory cautionary note. This range that I have shown here is pretty conservative. In the cosmology community, there are people who like to go really aggressive when it comes to deriving neutrino mass bounds. And it encompasses most reasonable variations in how the limits is extracted. So for example, assumptions about the background and various things. But let me also point out that if you are creative enough, it is actually possible to get around these bounds. And so, for example, there are people who have thought about a neutrino mass generation mechanism that kicks in at a very late time. Okay, so your neutrino mass will be essentially massless for most of the history of the universe, and you only generate neutrino masses at an extremely low redshift, say below 1. Okay, and in that case, if you have such a out there scenario, then it is actually possible to relax its neutrino mass bound to 1.5 electron volt. Similarly, if you deviate from Fermi-Dirac statistics for the spectrum of the neutrinos, you can buy yourself maybe a factor of a few if proven as well. Okay, so now I'm not saying that you should necessarily believe in these two particular scenarios because they are a little bit crazy, but I do want to highlight that there are assumptions going into these mass bounds, and while I work on this kind of thing, I think that an experiment like Katrin is extremely important and necessary because of the number of assumptions that you need to put into these cosmological analyses to extract a bound on a neutrino mass sum. Okay, so yeah, so that's that. Right. So future prospects. So at the moment, as I mentioned earlier, DESI just released their results recently. Their neutrino mass bound is not terribly different from what I just quoted. So that's why I didn't talk about them specifically. But let me also point out that Euclid, which is a European Space Agency mission, was launched last year in July. And the expected 1 sigma sensitivity to the neutrino mass sum from Euclid is something like 0.011 to 0.02 electron volt. They are, of course, also sensitive to the N-effective parameter to 0.05. Similarly, there's an American observation that's been in the planning for a long time, LSST. Their reported sensitivity to the neutrino mass sum is also more or less in the same ballpark. And of course, in the future, in the far future, there's CMBS4, and the sensitivity to the neutrino mass sum is also kind of similarly with N-effective. Now, so if you don't know what these numbers actually mean, essentially what they mean is that if the true neutrino mass sum is 0.06 electron volt from oscillations, then if you had indeed sensitivities that are so good, then a 3 to 5 sigma significant neutrino mass measurement may be possible in the next 10 years or so. Okay, so that's the forecast. Again, with forecast, there are assumptions going into forecast. So anyway, so we just wait here and see whether they actually materialize or not. But anyway, this is Euclid. It's actually a dedicated weak gravitational lensing survey, and they're looking for percent level distortions in distant galaxy images due to the photons coming from the galaxies being deflected by the large scale structure. So if you can see the distortion pattern and the statistical distortion, you can reconstruct the statistics of the large scale structure that lies in between, and from there you can measure the, any suppression that you might have coming from neutrino free streaming. And of course, the CMBS4, which has made quite a lot of news lately because it was recommended by P5. And essentially, it's going to be a series of 12 telescopes in the South Pole and the Chilean Atacama Desert. And they will not be surveying the whole sky, but they will only be surveying a small patch of the sky of about 1 degree. And they'll be focusing on measuring the polarization, the B mode in particular, because you can use the B mode and then because the B mode is mostly dominated by gravitational lensing, then you can use that to reconstruct the large-scale structure that is responsible for the lensing, and from there to pin down neutrino masses. Okay, so I have 50 minutes or 55 minutes? I say it says 10. Well, I wrote a talk for 50 minutes only, but no one minds if I finish early. Okay, so the last thing I want to say a couple of words about is CNUB and non-standard neutrino physics. So, so most of the discussion in the cosmology community at the moment, when it comes to neutrinos, cosmological neutrinos, is in pinning down an effective neutrino mass sum. But I want to remind you that there are other things that you can test with cosmology, and other things about the CNUB that you can test with cosmology. And in particular, one thing that we can do is to look for non-standard interactions of the neutrinos during CMB formation times, as well as large-scale structure formation times. And a couple of things that have been of interest recently are the ideas of testing neutrino self-interaction and neutrino decay. And well, I turned out to have more time than I thought I would, but in any case, I don't have a slide for neutrino self-interaction, but I do have a slide for neutrino decay. Okay, and so essentially the idea here is that if your neutrinos if they're relativistic, they decay while relativistic, and there's inverse decay as well, then this kind of backward and forward process can have a very strong effect on how gravitational potentials evolve during CMB times. And since the CMB fluctuations respond to these gravitational potentials, you can potentially see any kind of neutrino decay effects in the CMB. And now at the moment, we don't see any neutrino decay effects, so we can actually turn it around and put a bound on the neutrino lifetime. And at the moment, the CMB bound is somewhere here, about a few hundred seconds. Now, number probably doesn't mean anything to you, but if you compare this relative to, compare this with the bounds that you can extract from other experiments, the bound from BBN is about 10 to the minus 2 to 10 to the minus 1, from solar neutrinos 10 to the minus 5, and lab bounds are 10 to the minus 13, minus 11. So these bounds are so, well, not comparative that they don't even really feature on the plot. But having said that, however, there are bounds that are available coming from other observations that are comparative with the CMB bounds. In particular, those that are coming from IceCube and our neutrino telescopes. They are actually probing more or less the same parameter space as the CMB limit. So that's actually very nice because you don't really, these cosmological limits, you don't want the cosmological limits to beat everyone, right? So, it's very nice that there are actually other experiments that are also probing more or less the same parameter space. Okay, so I think that's all I have to say today about the CNUB. There's a lot more I can say about the CNUB, so come to the lectures. And I'll leave you here with my summary, and thanks for your attention.
So I wanted to ask you for the Euclid mission, you saw some number like 0.012, 0.02 for the sum of neutrino masses.
Yeah.
So as far as I know, for the Planck limit, it is 0.12. So what exactly those numbers are for the Euclid mission?
So these numbers?
Yes.
These are basically what I call 1 sigma sensitivity.
No, for this 0.011 and 2.02. So this is the expected sensitivity from this Euclid mission or what? For the sum of neutrino masses.
This is a sensitivity to the sum of the neutrino masses. So in other words, if my neutrino mass is 0 electron volt, what would be the 1 sigma error bar in that measurement? That's what these numbers mean.
Okay, so means from the Planck data, it is around 0.12.
Planck at the moment is 0.12, you're right, yes.
Yeah.
So this is basically, we're talking about factor 5 relative to Planck measurements in improvement.
So this is the expected sensitivity from this.
Euclid.
Yeah, it's not the current one.
Not the current one.
Yeah, it's expected from the Euclid mission.
This is an expectation from Euclid.
Yeah. Okay.
So if you combine Euclid, okay, so let me try to recall what was done in that forecast. Okay, so you combine that with Planck data, and then so you use Planck, because you almost always have to tag a CMB experiment on to anchor down some of the parameters, and then you add Euclid to the future Euclid data, then the sensitivity will go down to, the 1 sigma sensitivity will go down to 0.11 or 0.02.
Okay, thanks.
So factor of 5 improvement relative to Planck at the moment, more or less. Yeah.
There's a question here.
So thank you very much for your talk. What I wanted to ask is, there is some analysis of astrophysical data which has hypothesized that sterile neutrinos around the energy of, say, less than or equal to 7 kilo electron volts are possible candidates for dark matter. And those.
So was it 7 electron volt or keV? Okay, so the dark matter game is a little bit different, and the reason it's a bit different is that you expect the signature of keV dark matter to enter maybe here, okay? Whereas these large-scale structure measurements don't really, I mean, maybe with the exception of Lyman alpha, you don't really go that far, okay? So at CMB times, a keV dark matter is more or less like a cold dark matter, and you have to go to pretty late times down to a redshift of 4 or 5, and look at the Lyman alpha data to see if a warm dark matter like a keV dark matter is allowed. And I don't remember exactly what number is the, I don't remember exactly the bound on warm dark matter at the moment. It's always in the keV range. I don't know the exact number because they're always like 3 or 4 or 5, and there's some dependence on whether it's a thermal spectrum or maybe a slightly non-thermal spectrum, or maybe it's produced from decay. So there's some variation, but it's all in the keV range. So I think the 7 keV dark matter is probably fine from the cosmological point of view. Yeah. Yeah.
So it's mostly specified that right-handed neutrinos are mostly motivated for as right-handed sterile neutrinos. They are motivated as candidates for dark matter, but even antineutrinos, they have right-hand helicity. So how do we know that it's specifically sterile neutrinos that are more motivated for as candidates for dark matter and not antineutrinos?
Well, you mean like antineutrinos, but they still come with a mass that is light, right? If you're talking about standard model neutrinos.
Both of them do fall into the category
The main thing with dark matter is that you cannot have them in the electron volt range if they are to be thermally produced. Yeah, because they are just too hot. So that's the reason why you cannot have neutrino dark matter. They cannot be hot. Now, if you have a keV scale anti-sterile neutrino, let's say, I have no way to tell from cosmology because all cosmological measurements are only sensitive to gravitational effects, kinematics, basically. Quantum numbers are not something that enters into a cosmological observation. But in any case, what you mean is why is standard anti-neutrino not allowed to be a dark matter? That's simply because they're too light. Yeah, you produce neutrinos and antineutrinos in the same way by weak interactions. And when I talk about a cosmic neutrino background, that includes the anti-neutrinos, okay, that have a +1 helicity. And they're just too hot. Yeah. It's not the helicity, it's the mass.
Amol.
So suppose Euclid tells you an upper bound on sum of neutrino masses to be, let's say, 0.02, 0.03, and Dune tells us that
Yeah. Yeah, so actually, to be honest, one reason why I did not talk about the density bound is that I looked at the posterior. There's no peak around 0.05. I got worried. So okay, on the one hand, I'm giving these talks about cosmological neutrino mass bounds. On the other hand, I think we have to be extremely careful about what is claimed. Yeah. Sometimes it may be the cosmological model. Sometimes it's simply sometimes it's the analysis, how the analysis is done. Maybe people are too aggressive in combining data sets that are incompatible, and then you do the fit, and then the fit ends up in a compromised region, which happens a lot. Yet another thing that is going to be increasingly important to worry about is nonlinear modeling. So I don't have a slide here, unfortunately, to show that, but this picture here is actually slightly misleading in the sense that the power spectrum is computed from linear perturbation theory. But perturbation theory today breaks down around here. So essentially what it means is that all of these observables here are nonlinear in some ways. And nonlinear modeling can be highly non-trivial. Yeah, collision nonlinear modeling is easy. You just run in n-body simulations. But if you want to model something like Lyman alpha, you have to worry about star formation, supernova feedback, and these are things that you can't calculate from a Lagrangian. You have to rely on someone's astrophysical model to feed into your simulation to get a prediction for the power spectrum, and then you come back with data. So that is my biggest worry, whether these models are believable. So if someone comes up with a neutrino mass sum bound of 0.02 or whatever, I would say that most likely there's something wrong with the theoretical modeling. So yeah, so we need to be very careful. I'm kind of getting increasingly, skeptical about some of these bounds myself. And one reason, as I said, is because at some point when you do a fit, and if you know that there's a neutrino mass signal at 0.05 electron volt, I should be able to see a bit of a peak. And so far, I haven't seen anyone returning a fit with a little peak around 0.05. So I'm actually getting a bit worried myself, to be honest. Yeah.
There are two questions from online audience. Joseph Samuel, you can unmute and maybe ask the question.
Yes. Neutrino oscillations have a CP violating parameter. Does this leave any cosmological imprint?
Yeah, so in principle, you can change the prediction of this n effective parameter. If there's some minor bit of, if there's some CP violation, you can shift it a little bit. But it would only be a very small effect. So at the moment, corrections to n effective of 3 is only at the percent level. If you add CP violation to that, I think it might only affect that parameter at maybe the 4th or the 5th decimal place. That would be my guess. Now, of course, if you start deviating a lot from the standard model, and suppose suppose the CP violation gives you a large asymmetry in the neutrino sector, then you could have a bigger effect. But if there's no amplification of any asymmetry, if there's no initial asymmetry, then having this CP violation parameter being non-zero wouldn't really do that much.
Thank you.
There's another question by Manoj Viknesh. You please unmute and ask your question.
Hello, can you hear me?
Yeah.
Okay, so I was wondering if I can interpret this figure, especially the lower power at small scales, as due to lower density of cold dark matter rather than some neutrino physics?
Well, it is because of the, you do have lower density of cold dark matter, but the total dark matter density is the same, okay? Because the neutrinos are already non-relativistic. They are just non-relativistic, but with a bit of non-relativistic velocity that allows them to disperse. Okay? So the more correct statement is that this suppression is due to the lack of non-clustering dark matter, yeah, rather than just, matter, non-clustering matter. That's the reason why you're seeing the suppression. Do I answer you, or have I understood you correctly?
Thank you.
Yeah.
More questions? Oh, there is one. Just wait. Just wait for this.
I would like to ask that the value of summation over mu sum of the neutrino masses, are there any dependence of the hierarchy of the neutrino mass, like whether the neutrinos are like inverted or normal hierarchy, or if this so I mean, what are the cosmological preferences of mass hierarchy of the neutrinos?
Okay. So most bounds that you would find in the literature assume all neutrino masses to be the same, degenerate. Okay? And the reason they make that assumption is because calculating CMB spectra or these CMB spectra and meta-power spectrum with neutrino masses is quite time consuming compared with just massless neutrino cosmology, because you have to solve a lot more equations. And every time you add a new mass to it, you have to solve more equations. So if you have three masses as opposed to three different masses as opposed to one mass, you're basically making it 3 times more equations you have to solve. So I'm only aware of one group that has even bothered to do that exercise because it's so time consuming. And the end result is that, yes, there's some variation in the mass bounds depending on exactly which hierarchy you assume to do the fit. But the mass bound variation is maybe of order 20%, 40, 30%, something like that. So not huge. Okay, so Planck says 0.12. That assumes a degenerate mass spectrum. If you change that to inverted or normal hierarchy, maybe you get 0.15 instead. Okay, so not a huge effect. Yeah, so I'm not sure if I answer you, but that's a variation, yeah, that we have at the moment.
The recent DESI survey data, they have some slight preference of the normal hierarchy. So of the some of the neutrino masses.
Do they have what? Sorry.
The recent observations of the DESI data.
Yeah.
So there are some.
There's no real preference. No, there's no real preference. There are people who like to say there's a preference because they like to do Bayesian statistics and model selection, but they're really just measuring their prior. Sorry, I've said it. No, I don't want to name names, but but there's no preference. No, really none. Yeah, we can talk in private.
There was a question here.
You have to speak up a bit. Yeah. Yes. So there will be a cosmic background for this. If you make them, yes. It may be there. Yeah. Should it be colder or hot? 1 electron volt. It's a hot dark matter. No, I mean, should it be colder than the CU? Oh, right. Okay, got you. Yep. Okay, so it's a question of so it would be more or less the same temperature as the standard model neutrinos. And the reason is that if you look at how, if you're talking about like this short baseline sterile neutrino, which is 1 electron volt, and the mixing is not hugely large, but it's quite a bit of mixing. Sine squared 2 theta is what, 10 to the minus 2, something like that. So people have done this kind of calculations for a long time. What you normally get if you assume those mixing parameters and mass splitting is essentially a 4th neutrino species. So you change this n-effective parameter to 4. And the spectrum of sterile neutrinos that you would get is essentially like standard neutrino. So it will be Fermi-Dirac It has the same temperature as the standard model neutrinos. And the reason is because the way you're producing this background is via the active neutrinos. Okay, so you basically have an active neutrino oscillating into a sterile neutrino, and then the active neutrino gets repopulated from the background. So whatever you produce for the sterile neutrinos would basically have the, it's basically transferring the properties of the standard model neutrinos to the sterile neutrinos. So in the end, they will be more or less the same temperature, more or less the same energy distribution. It wouldn't be colder, it would be the same. Yeah, because you're getting this, you're producing this background from the thermal bath, and therefore these sterile neutrinos will pick up the same, more or less the same properties as the thermal bath. Yeah. Yes, it will. It will be. It will basically add to this N effective parameter. It will add about 1. So instead of 3.044, you will have 4.044 or some small variation, some small correction. Yeah, that's basically the answer. Yes. Yeah.
Okay.
Yes.
More
So
questions?
sterile neutrinos are strongly constrained. Light sterile neutrinos are strongly constrained by cosmology.
Hi. So I just want to ask a follow-up question.
Yeah.
You said that if the sterile neutrino produced from the thermal bath, then it have the same properties.
Yeah.
But if it produced non-thermally, then?
Non-thermal in what sense?
Like
Decay or what?
like Dodelson withdrawal mechanism.
From what side?
Dodelson withdrawal mechanism
Yeah.
is a non-thermal production, right? They don't have anything connection to thermal bath.
So, so if you want the anything cosmologically produced to not have more or less the same properties as the background, then you need to really completely decouple it. So from the background somehow. So any kind of scattering process where you're producing this relic from scattering of something, as long as that scattering is somehow tied back to the thermal bath, you will have the property of the thermal bath. That's very generic. On the other hand, if you produce these sterile neutrinos from, say, decay, then, and the particle that's decaying is completely cold, then you can get rid of this dependence, because then the property of the relic will be dependent on things like the mass gap between the parent particle and the daughter particle. Otherwise, most things, I think I'm saying it very generally, but most things that most relics that are produced from scattering, you will, at some level, pick up the properties of the background. So let's say for example, this KeV sterile neutrino dark matter that people talk about, they talk about non-thermal production, but even that is not completely non-thermal, because yes, the background is not like a nice thermal Fermi-Dirac distribution. It has some funny shape, but ultimately, the energy, the average energy of those particles is still reflecting the bath from which they have formed from scattering. So non-thermal KeV sterile neutrino bounds are still in the KeV range. Yeah, maybe a little bit different from the thermal sterile neutrino bound, but they're still in the KeV range for that reason.
Thank you.
Yes.
Are there more questions? Oh, okay.
So relic neutrinos, these are those neutrinos which was hot before and now it is cold, right?
It's still hot in it's relativistic before, now it's non-relativistic, but they are still
Yeah, my question
hot.
is, so these are the dark matter candidates.
They are not dark matter candidates because they're too hot.
Okay, so I would just like to know that why massive neutrinos are only dark matter candidates, and why not we can consider solar neutrinos or any other neutrinos to be.
Hang on, I don't completely get that. What about solar neutrinos? I didn't get the part about solar neutrinos.
Solar neutrinos or any other neutrinos to be dark matter candidates.
Well, there are not enough solar neutrinos to begin with. I'm not.
So his question is why the neutrino is massive. Low mass neutrino could also be dark matter.
Yeah.
So that's his question.
Yeah,
So
that.
Dark matter is a massive neutrino.
Yeah.
But if it's a low mass neutrino, can it be a dark matter candidate?
Low mass neutrino, can it be a dark? Well, it cannot be the dominant dark matter candidate.
But
Because they okay. So the simplest reason is that you make these things, when you make them, they're very hot. They're relativistic. Now you can rely on redshift expansion of the universe to make them colder, but at some point, well, you know, they do become cold and they do become non-relativistic, but they're never really cold enough. Okay, because we have seen all these structures like dwarf galaxies and galaxy clusters. And in order to make these objects, you need to be able to pack these dark matter particles into a fairly small region of space. Okay, so for example, if I look at the Milky Way, the Milky Way has a mass of 10 to the 12 solar masses. It's packed in a radius of maybe about 50 kiloparsec. Now I can ask myself, if I have neutrinos that are really hot to begin with and they cool down, can I just from phase-based arguments, can I pack these neutrinos in such a small space? And the answer is you can't. Yeah, because the neutrinos, apart from adiabatic cooling, they have no way to dissipate that energy. So for that reason, a standard model neutrino, which is maybe about electron volt or sub-electron volt in mass, cannot be all of the dark matter. Yeah, because we have seen galaxies, and such a dark matter would not allow us to form galaxies. Okay? Much less dwarf galaxies. Maybe you can get a galaxy cluster out of something like a 10 electron volt neutrino, but you just cannot. Yeah. So I'm not sure if I'm answering you completely.
Yeah. Maybe we can take one last question from online. Ram Prasad, can you unmute yourself and ask the question, please?
Yeah, sure. So actually my question is going to be relatively simple because I'm 7th grade. So solar, can we use solar neutrinos to detect the changes in the sun?
Solar neutrinos to detect changes in the sun.
The chemical reactions.
Oh, do you have enough statistics? I mean, is there a solar neutrino expert around here who can answer that?
Sorry, I don't get you.
Depends on it, yeah. I mean, you need enough events to be able to monitor these changes, right? Yeah. Yeah.
Yeah, so the current largest detector to detect solar neutrinos detects about 5 neutrinos per day, 5 to 10. And that number is too small for us to say anything about what's happening inside the sun. But if something strange starts happening, I think Andre has some work, right? No, sun starts producing GeV neutrinos, then something else will see.
Yeah, so it's the same answer. Basically, unless there's something very dramatic happening on a time scale of weeks or years, we're not sensitive to that because we don't have enough data. And it's one of those things that people get excited about because the light that comes from the sun is very old, and the stuff that comes from the neutrinos is instantaneous. So people always wonder, maybe the sun is dying on the inside and we don't know yet. But the neutrinos don't reveal that, at least with a time scale of some period of time that's related to how much statistics we have. And we've only been collecting data for a few decades, so it's not a great amount of information that we have.
Yeah, okay.
Okay, I think let's, maybe you can catch her after the talk, okay? Yeah, so we are running out of time. I am sure there are lots of questions. So let's thank Professor Yvonne for a nice talk.